Hi, this is lecture 6 of our Physics 332 course at Binghamton University. This is to complement your lecture notes and allow us to have more examples in class. Today this talk will be on dealing with RLC circuits. This builds on from our understanding of inductance, mutual inductance, how inductors differ from capacitors. I'll assume that you appreciate the difference between a capacitor and a resistor from your electrostatics. We will then use our understanding of EMF to consider an actual circuit and solve it within within Faraday's law. So we're going to consider a simple circuit where there is a source of EMF and an inductor. That builds on from what we've previously done. And we now know that when there is for instance, a solenoid as a good inductor, what we have is if we change our current, there'll be a change of magnetic field. We can describe the induced EMF in Faraday's law. Here we have Faraday's law for our circuit, and we consider the path to be essentially our circuit. It's good to remind us of what we've learned from electrostatics. In that case, if we were considering a circuit, the electric field would be conservative, so then if we went around the loop, it wouldn't matter which direction we went around, it would be path independent. We now have a non-conservative magnetically induced electric field associated with the change in magnetic field, and so our EMF is path dependent, so it depends which way we integrate around our loop. I am going to consider a very simple circuit. It's going to be a source of EMF, an external source like a battery. There'll be a resistor that describes the total resistance. We're going to consider that in series with our battery, and then I'm going to have a huge circular loop, not an inductor, just a big loop. The reason for that is we're going to start off simply and go from there. The loop is supposed to be much larger than the rest of the circuit, so then we can assume that if we integrate the magnetic field through a loop associated with the circuit, we can approximate the magnetic field inside the loop as pretty close to the total magnetic flux. And we're going to choose dl of our path loop to be in the same direction as our current for simplicity. So what we have is we've chosen the magnetic field. We've chosen a magnetic field which relates to and chosen our surface associated with our loop to be parallel to make things easy for our integration. So we're going to imagine that we turn on a switch. Current will flow. It will flow in the direction that we've shown, and we need to consider what that current is, and what we have to do is explicitly integrate the path integral of E dot dl, and here we go. We're going to break up our integration. First off, we'll consider the E dot dl across our battery, which we will say will be moving against our electric field because it is providing our source of current, so it has to fight against charge separation, and so that's given as minus our E sign that I use for external EMF. Next, we consider the potential difference as the E dot dl across our resistor. Our resistor will be such that we can relate that as our voltage drop, because although E dot dl across our entire circuit for a conservative electric field is equal to 0, we get the same result as we do in electrostatics, where this potential drop is equal to IR. And this will be positive, whereas before we had a negative sign for EMF, because the electric field across the resistor will be in the same direction as the current, and we're using the current as a positive direction around our loop. Next we consider our large loop. Our large loop, we're going to say that the resistance of the wire is equal to 0 because we've included all the resistance in our resistor term. There must be no electric field because it would be a perfect conductor, and Ohm's law says that E dot D that we would have no electric field. So our total E dot dl around our loop, if we have a in a steady case, would certainly be our EMF and our voltage drop across our resistor, so we'd get our EMF equals IR, as we'd expect. The signs are associated with the direction we've chosen to go around our loop. But now we have a current going around our loop, there must be a magnetic flux. And that magnetic field associated with the current must be cut through our surface, associated with an open surface associated with our bound loop, which we're assuming is mainly described by the big circular loop. From our geometry, we'd expect that. So what I've tried to show here is the assumption that we're trying to do that. The rest of the circuit makes a very small contribution to the magnetic flux. This makes it easier for us to solve Faraday's law. When the switch is turned on, our magnetic flux will increase. This is because of the way in which we've chosen our surface and the positive direction of our loop. So then ds is pointing in the same direction as B. What we can then do is say that, well, we'll combine all these together. So now we've done our E dot dl around our loop, then we must consider the magnetic flux on the other side. This means that we take the E dot dl around our loop. Remember, our loop has no electric field. For a perfect conductor, we're only going to consider the magnetic flux associated with the coil inductor, single coil inductor. So here we have our integrand around our loop in the counterclockwise direction, and then this must equal the magnetic flux that goes through. So we can relate that to our inductor, and so our voltage drop across our entire circuit must be our external source of EMF, the current, the voltage drop associated with our resistor, and then our inductance term, and this is equal to 0. So you can see now that we have a differential equation associated with a time dependence on our current. When we don't have a time changing current, we reduce back to our simple circuit case. If we look at this equation, what we can do is we could view this as a modification of our static case, where if we viewed this as a EMF itself, then if we summed all the EMFs together, we would have E total equals IR. And so it would look as if we have our original electrostatic path integral. And so this is referred to as Kirchhoff's modified loop rule, where we can consider all sources of EMF together, and that's why we are going to put the to make this equal to 0. So let's describe this a little better. We can view it as when we turn on a current, there's going to be a current flow. We can imagine that instead of having an inductor, we just add an external source of EMF that opposes the increasing current, and this is shown by analytically below. Likewise, if our current was decreasing in time, say we turn the switch back off, and we can imagine that there we've added another, instead of having an inductor, we've just added an external source of EMF like a battery, which would be trying to oppose the change in the current. And so we'd have the following expression if we measure the voltage drop across that coil. So now we're at a point where we can describe an RL circuit. We've not considered a current capacitor at this stage. What we can do is replace our RL circuit with a case where we view it as there's two sources of EMF. We have a battery and an EMF, an external EMF, instead of our inductor, which has a potential drop across A and B. Then we can use Kirchhoff's modified loop rule. And so we can sum up the battery EMF and the inductor EMF and consider the voltage drop across our resistor to total equals 0. This gives us an expression here, which we can then rearrange to integrate. If we impose a condition, boundary condition, that our current is equal to 0 at the start, we can then solve. And this is shown here. So I'm just going to move the diagram a little bit further, and what we can see is our current displays an exponential form. When t goes beyond a certain characteristic time, we then have a situation where we tend to our steady state solution, which is just relating the current to the external EMF and our resistor. And down here you can see that the inductor would dominate if we plot as a function of time. This characteristic time is determined by the inductor and the ratio between the inductor and the resistor. So you can change this by, you can increase the characteristic time by increasing the inductance of the coil, or so making more coils, because we saw that depends on n, or playing with the radius, or we could reduce the resistance of our wires. Typically it's easier to just play with the inductance by adding more coils. Instead of considering in terms of current, we could view it in terms of change of our net effect EMF, and we can see that the reason for this is our EMF would vary with an exponential decay because of the exponential form of the inductance. So what we could comment from a physical point of view is that self-induction disappears as we it vanishes with time towards our approximation of a steady system. We could also consider a decaying current, where we have a stable current and then we switch a switch. So then the current began off in the external battery EMF divided by R as our steady current, and then we can describe how the current will tend towards 0. So this is plotted below. So here's a schematic of it. We have a source of EMF. We are going to close a circuit here to short the inductor and the resistor. So short off the battery. So then we just have a loop here. We consider the current flowing through this part. To begin with, this current is going to be decreasing in time, so we can replace our inductor with a battery in this orientation, thanks to Lenz's law, and we can write our expression as having an EMF plus an IR is equal to 0, such that we have this expression. Rearranging, we have a differential equation that we can solve. We then impose the fact that we had a stable current at time equals 0. We again obtain our exponential form. This time it's a decay, and we have the same time constant. So if we want to make this a quicker decay, we need to increase the inductance. Reduce the inductance to get a shorter time. I apologize. That's the opposite. So this will increase as we increase our inductance. So now we feel comfortable with the previous description, where we had a case where we could view it as we had a current but no external battery. We can view a decaying capacitor in the same way. We've charged up a capacitor, we have a switch, we're going to consider the capacitance of our capacitor, which we've done before, because V equal voltage equals the expression Q equals VC, so we can rearrange here, and then we have our inductance, and when we close this switch, these are our two contributions. Then we can build on the notes we had regarding energy considerations. So to begin with, our capacitor is got all the charge, and when we close the switch it discharges, so we know that our electric energy is ½ Q squared over C, and that this current is created by this discharge, and then we end up making a magnetic field in our inductor because the current is changing with time, and as a result our magnetic energy becomes stored in our inductor and is given by this expression here. In the absence of a resistor, there would be no dissipation of the energy into the outside the system, so we can consider our total energy as that from a contribution from a capacitor and from our inductor at any time. So we have half q squared over c and half l I squared. So then what we can do is consider the change in our energy, total energy at any time, given by this equation here, which then gives us a differential equation. This part here must be equal to 0 because there's no change in our total energy, because there's no dissipation of energy for a resistor, and so we end up with this equal to 0, in which we can then solve. We remember our differential equations. We know that this is a nice regular second order ordinary differential equation. We comment on the sign here, and this is to do with the fact that one stores energy while the other one releases energy. We remember then this equation, we can use a general solution where instead of current now we're dealing with charge as a function of time, because current is equal to q over dq over dt, so we've got a second order differential equation with q instead of I. Then we'll have a frequency dependence, and what we find is that frequency will depend on our RLC term, which gives us a characteristic time, and our current, once we've got q, then our current can be determined, and we have an oscillating current. Here we try to show the oscillation of the charge and the current. You can see the current is large, and then the decays, and then the current increases, so they're out of phase by pi over 2. So what we can do is expand our energy contributions now that we have expressions for these, and show that our energy does oscillate nicely between storing all our field in the capacitor and all our energy in the inductor. So here we have our total energy as we oscillate between the magnetic field energy and the electric energy. The rest of the notes describe the case where we have a dissipation of heat from our resistor. So we now move on to considering RLC circuits. In this case, current still oscillates between the capacitor and the inductor, but we're going to lose energy through our resistor. This is shown here. We have our power dissipation from our resistor, which is going to be our Joule heating loss, and so instead of having 0 at this point here, we now have an I squared R. This means that our differential equation is modified, and but we can still consider a general solution where we include a damping term in addition to our oscillating behavior, and that damping term depends on the ratio between the resistor and the inductor. One final note is when you tend your resistance to 0, we get back to our original situation where our characteristic angular frequency is related to 1 over our inductor and our capacitor.